Welcome to the 7th episode in a series for calculating pi on my relay computer. Here's the journey so far. And it started with a challenge to calculate pi to 20 decimals, but on my relay computer, my basic, limited, electromechanical 8-bit relay computer. And although that all sounds like asking for trouble, we're actually making pretty good progress, and therefore on with a goal, the precision of pi that my computer needs to calculate. How so? Well, you've hopefully seen the series so far, so know this next bit. All together, with the binary-friendly infinite series, the Bailey-Borwein-Plouffe formula, or BBP for short. Tiny issue though, BBP produces pi in base 16 not decimal, but we can convert between the two, so no problem. And so I converted the BBP formula into high-level pseudocode, and built up a shopping list of the functions needed, that is, the things my relay computer can't do natively. In the most recent episodes we've been able to tick a few of these off, and we've now got long addition and long subtraction in the bag, along with the basic add increment operations, which are easy peasy. So where's that got us to? Well, it's the bit I've been dreading, long division. Actually no, that's a bit strong. It's not keeping me awake at night paralysed with fear or anything, but division is one of those things I've historically left to the calculator, so not only do I need to relearn it myself, but I also need to work out to do long division in binary on my relay computer. There's no avoiding it though, as looking at the BBP formula there's plenty of division, and it's a big part of calculating pi in pretty much any approach. Now, fair warn, this is going to be a challenging episode, certainly for me, but maybe for you too, but I'll do my best to explain what I've learnt. So onwards, let's nail this. And let's start with something simple, 9 divided by 4, that is, how many times can you fit 4 into 9? Well, this one is quite easy to calculate in your head, and personally I just recalled my childhood times tables to know that 2 4s are 8, and then 9 minus 8 is 1, so the answer is 2 with a remainder of 1. What's interesting here is that the remainder of 1 represents 1 of 4, a quarter, and a quarter is 0.25 in decimal, and actually if you do 9 divided by 4 on a calculator you get a result of 2.25. So that all adds up. Simple, yeah? Next, let's try 90 divided by 4. Now again, you can pull mental arithmetic tricks to calculate this quickly, but long division by hand takes us the following route. We start with a tens column and consider how many times does 4 fit into 9? Well, we already know that's 2, so that goes at the top, and we can then subtract the 8 that 2 times 4 represents and get our remainder of 1, just as before. We can now pull down the units column to make our remainder become 10, and we consider how many times 4 fits into 10. Well, that's 2 again, totalling 8, with 2 as the remainder. So 4 fits into 90 22 times, with the remainder of 2. Again, that remainder is 2 of 4, 2 quarters, so 0.5, and therefore the full decimal answer of 90 divided by 4 is 22.5. OK, let's up the units and go with 900 divided by 4. Well, long division is just as before, and for our last digit of the result we have 20 divided by 4, which is 5, and when we subtract the 20 that 4 times 5 represents, we're left with a remainder of 0. Our answer therefore is 225, and 4 times 225 is 900 exactly. Out of interest, what happens if we try 9000 divided by 4? Well, the process is exactly as before, and for the last digit we have 0 divided by 4, which is 0. And we know here that no matter how many more digits we add to the right of our dividend, our 9000, the result will end with corresponding zeros. So, why am I taking us through all this primary school stuff? Well, remember that we're going to be using fixed point binary numbers in our pi calculation, and so it's worth considering what happens introducing a fixed point like so. In this example we're calculating 9 divided by 4 again, but want 3 decimal places of precision. The long division is identical to 9000 divided by 4, but we're just marking our decimal point after the first digit. Note that the divisor, the 4, stays exactly as is. We don't scale that in any way, but naturally enough our result is 2250, or with our decimal point 2.250, which is what we're expecting. 9 divided by 4 is 2.25. Right, for our pi calculation we'll generally be dividing smaller numbers by larger ones, so let's take a look at the inverse of our example here. So this time we're going to do 4 divided by 9 to 3 decimal places. Let's work it through. 9 into 4 won't go, so our first digit is 0. Next we look at 9 into 40, which goes 4 times for 36 remainder 4. We drop the next 0 of the dividend down, and 9 into 40 goes 4 times again, for a total of 36 remainder 4. We can see here that we're trapped in a repeating pattern, and as such, we know every next digit will be 4. So, 4 divided by 9 is 0.444 recurring. Right, let's try that in binary. The divisor is simple enough. 9 in binary is 1001, and just as with decimal division, no scaling of the divisor is needed. Things get interesting on the dividend though. We know that 4 as a binary integer is 0100, and just as with decimal division, we can scale out the number with zeros so long as we keep close track of where our binary point is. What we do need to do though is ensure our dividend is aligned with our divisor. Currently we have a dividend of 4, but if we started our dividend with 1000, then that's a decimal dividend of 8. If you wanted a dividend of 16, well that'll still be 1000, but would then need to keep track of a leading 0 on the divisor to ensure that when we do the long division, we're using similarly scaled values. Otherwise we'd be dividing by 18, not 9. This bit still hurts my head a bit, but does make sense in the long run. If we get the positioning wrong and did have a dividend of 8 rather than 4, our result, the quotient, would effectively be double what it should be, because all the bits would be shifted left one place. We'll come back to this shifting concept shortly, as we can use it to our advantage, but for now let's work through this example of 4 divided by 9. Arguably, long division in binary is a little easier than decimal because each time our question becomes, is the divisor less than or equal to the remainder so far? So 1001 is greater than 0100, so it doesn't go and we get a 0. 1001 is greater than 1000, so it doesn't go and we get another 0. Next, 1001 is less than 10000, so it does go and we place a 1 in the result. Just as with decimal division, we now need to subtract our divisor, which will always fit once or not at all, because our binary result bit can only be 0 or 1. Subtracting 1001 gives us 0111, and conversely of course, 0111 add 1001 is 10000. Here I've done the binary subtraction in my head, but the computer would take a 2's complement of the divisor and add it of course. As with decimal division, we bring the next binary digit down to give us 1110, and a divisor is less, so we get another 1 in the quotient result. And we could subtract the divisor to get 0101. Again we bring down the next 0 to arrive at 1010, and we could subtract our divisor again, resulting in a remainder of 1. Now what's interesting here is we've effectively entered another long division loop, as our remainder now matches our starting dividend. And we would get 3 more zeros in the quotient result before arriving again at a remainder of 10000. After that, the pattern repeats with 3 1s, 3 zeros, and so on. So, just as our decimal division resulted in a recurring 4, we ended with a repeating binary pattern. And our result is as follows, where the 2 dots mark the start and end of the repeating sequence. The nice thing here is we can just keep going with the long division approach to capture increasing precision and more fractional binary digits. Probably worth at this point spot checking our result and making sure it's what we expected. Looking at the resulting quotient, we have bits set in the negative powers of 2 at 2, 3, 4, 8, 9 and 10. In other words, bits set in the quarter, 8th, 16th places and so on. If we add those together, we arrive at a decimal result of around 0.444. If we continue the recurring pattern and add even more fractional terms, we get even more precision, somewhere around 0.44444. It's important to note again that 4 divided by 9 in binary and decimal don't result in exactly the same value, because of the way the numbers are represented as fractional powers of 2 and 10 respectively. Right, let's take a look at that handy shifting concept I mentioned earlier. And here's our 4 divided by 9 example again, but what about if I want to calculate 2 divided by 9? Well, we know the resulting decimal would be half of the 4 by 9, so 0.222 recurring. If we look at the binary equivalent, we can see it's similar to the 4x9 example, but each bit of the dividend and quotient has moved one place to the right. It's got smaller by a power of 2. It's half the value it was. It's divided by 2. Similarly, for 1 divided by 9, we expect a decimal result of 0.111 recurring. And binary-wise, we've moved one place to the right again. That means, with our binary calculation for 4 divided by 9, we can quickly get 2 by 9 and 1 by 9 with bit shifts. If we look at the binary fractions added up, we can see we get pretty close to the decimal results expected. The reason for the bigger gap this time is because we're only using 3 fractional terms in each binary quotient, but if we calculated the division to a greater precision, our result will get closer and closer to the decimal results. Along with shifting right, we can go the other way too, of course, and we could even skip all leading zeros in the dividend as long as we keep track of where the binary point needs to be. This can be quite handy because we could just count the leading zeros and start our quotient with the same number of leading zeros. In the example here, that will be equivalent to calculating 8 divided by 9, but the key point is the train of binary digits will always follow the same pattern for a given divisor. Right, so we've seen long division by hand, but what do we need to make it a bit more palatable for my relay computer? Let's work through 8 divided by 9 this time, which is, of course, just left shifted from our previous 4 by 9 example. To start, let's set up some registers for the division, and we'll go with the divisor first, which we'll put into register M. Now note these registers have nothing to do with those of my relay computer. Here it's purely just a naming scheme for the purposes of this long division example. We'll also set up a -m register, which has the 2's complement of m ready for subtraction through addition. Next we have A, which starts with 0, and Q, which starts with a dividend, but the plan is by the end of the routine, Q will contain our quotient result. Finally, we have C, which is our loop counter, and starts with the number of bits in our dividend. So 8 here. We're all set up for our first iteration, and we take the following steps. First, we shift A and Q together as a single register, discarding the most significant bit of A and bringing 0 into the least significant bit of Q. Next, we subtract M from A, that is, we add -m to A, and if A is less than M, then A would now be negative, and indeed that's the case here because the most significant bit is 1. The reason that works is although A has 8 bits, we're treating it as a signed 7-bit number. This means, of course, that if the value of M was larger than 127, we'd need A to be 9 bits long to accommodate the sign bit. Now, because the sign bit of A is set, we know M doesn't divide into the current value of A, and therefore we know the next bit of our quotient is 0, and we need to undo the subtraction. That is, we restore the value of A. Finally, we can decrement the C counter, as that's our first iteration complete. We now repeat by shifting AQ left, subtracting M, then checking if A becomes negative and restoring if it is. This continues on until we reach the point where A remains positive. In this case, we don't restore and set the next bit of the quotient to 1. Let's continue to the end of the loop, and there's our result. Actually, that's not right. We can see the start of the 11100 pattern, but there's 4 leading zeros, not the 1 leading zero expected. What's going on? Well, I've failed to keep track of my binary point. Take a look at the value of the A register after the first AQ shift. That's our starting remainder, which is 1 and not 8. So what I've actually done here is calculate 1 divided by 9, and indeed the resulting quotient is that instead, with the binary point after the first most significant digit. So how do we get the result we wanted? Well, we'd need to shift our starting position. So this time we'll start by shifting AQ 3 times before entering the loop, and iterating that all through. By the end, Q then contains the value we wanted. Again, the resulting bits will always follow the same pattern given the same divisor, but by shifting our starting value, we control how the resulting quotient is shifted. This trick is quite handy, as I'll show later, but it does mean keeping track of the binary point is crucial, and of course, you can only do this with dividend leading zeros. It's worth noting also that although we've only been moving zeros into A at each AQ left shift, this process still works for dividends with subsequent non-zero bits, So if our dividend was 9, 10, 11 and so on, the approach here still works. We're just sticking to powers of 2 because we know that our dividend is only ever 1, 2 or 4 in the BBP fractions. What I've shown here is an approach called restoring division, so named because at each iteration we restore the remainder if subtracting the divisor resulted in a negative value. There is a related approach which is also worth covering called non-restoring division. Now, arguably this approach is more complicated to manage, but it removes the extra calculation step of undoing the subtraction of m that appears in restoring division, so it can be faster on some computers. We start with a, q and c the same as in restoring division. Next we need to decide if we're going to be subtracting or adding m to a. If a is currently negative, i.e. the sign bit is set, then we'll be adding m, and if it's not set, we'll be subtracting m. In this case a is positive, so we'll be subtracting m. With the decision made, we can then left shift aq as before. As decided, we then subtract m, and if our resulting a is negative, then the next bit of the quotient is 0, if it's positive, then the next bit is 1, similar to what we did in restoring division. In the next iteration, a is now negative, so we'll be adding m this time, which results in a becoming positive, so the next bit of the quotient is 1. We repeat this all the way through, and by the end we have our same result. Something we have to be careful with though is the value of a at the end, our remainder. For non-restoring division, a is stored in a non-standard redundant form, where the bits represent -1 and +1 rather than 0 and 1 as you might expect. As you can see throughout the calculation, we therefore sometimes end an iteration with a remainder in its -1 digit form. In binary though, we can easily get back to the real remainder with a 1's complement in those cases. Fortunately for our pi calculation, we're not at all interested in the remainder, so we can happily ignore it. Okay, creating these slides is making my eyes go funny, so let's have a change of scene and revisit our dotnet pi code again, as I think it would be good to replace the native dotnet division with our non-restoring equivalent here. If we can get the same pi result as before, then we're heading in the right direction. So here's the before and after view of the dotnet BBP pi calculation that I've walked through in previous episodes. So far I've been calculating the BBP fractions using the implicit division provided by dotnet's big integer class. This gives exactly the results we need, but we can't really see how it's performing that division. Well, actually that's not true. This being .NET, the full source code is freely available, but the point is my relay computer doesn't have native division capability, so really we're best to implement our own division routine here to get confidence for writing the assembly long division later. On the right here you can see I'm calling a new reciprocal method. Beg pardon? I thought we were doing long division. Well, if you look at the BBP formula again here, you can see that in terms of division we can get away with using a dividend of 1 and then just use left shift for the dividends of 2 and 4 as we saw earlier. So in the first iteration we'll be calculating 1 over 1, 1 over 4, 1 over 5 and 1 over 6, and these are reciprocals of 1, 4, 5 and 6 respectively. The other reason we calculate reciprocals is because it allows us to make some optimizations in the division routine. In our non-restoring example just now, we shifted A and Q as one unit, but actually because our dividend is 1 followed by all zeros, we could left shift A and Q independently and have Q as long as we needed. Now don't worry if that's not making sense just yet though, as you'll see in a bit the running .NET code building the quotient up. For now though, splitting A and Q does set us up nicely for the precision parameter here. This will set our C loop start value and effectively therefore tells the reciprocal method how many bits we'd like in our quotient result. In all cases our A register will stay the same size, but we can have Q as big as we like. What's curious though is the first reciprocal has an extra 2 places of precision, and the second an extra 1 place of precision. Well, that'll have the effect of left shifting the quotient by 2 and 1 places respectively, which saves us additional shifting operations. Right, let's take a look at the reciprocal method itself, which closely follows the non-restoring division approach we just looked at. We start by setting up our A and Q registers and then enter the C loop. At each iteration we check the sign bit of A for our add or subtract M decision. We then left shift A and Q separately, and on the first iteration we set the least significant bit of A for our dividend of 1. We can then add or subtract M as required, and finally we set the next quotient bit depending again on the sign bit of A. That's it. I've also added a verbose option here, which will give a readout of the intermediate results as the quotient builds up. So let's enable that for the fourth BBP division and give the code a run. Now this is going to get a bit busy with verbose mode switched on, but first let's check our final result of pi at the bottom here, and excellent. It's still coming out with a correct result, so I've not broken anything. Scrolling up here on the last iteration, we've got the fourth BBP fraction of 1 over 134. And just above is the output from the reciprocal method for the same. The columns, left to right, are the current C loop register, then the A remainder, and then our quotient Q building up over time. At the far right is the hex equivalent of that quotient. You can hopefully see here how increasing the C loop by 1 or 2 will effectively shift the quotient left that many places. We get additional precision at the right, of course, at the same time. Cool, okay, that's given me a bit more confidence in the non-restoring binary division approach, and as before, all this code is available in my GitHub repo, link in the video description below, so if you want to have a play, feel free. Right, I now need to convert this into my relay computer assembly language. Before I can do that, we need to quickly game plan the approach, because as always, one big challenge we face in programming the relay computer is a limited number of registers available. So we might need to get creative to work around that. Let's take a look-see. And how about this for an assault on the eyes? This is, of course, the full bit-by-bit build-up of 1 divided by 134 that we just saw produced by the dotnet code. The resulting quotient is 76 bits long, which is 19 hex digits and therefore 9.5 bytes. The irony is that in each iteration of BBP, we right-shift our intermediary result by 4 times k, so the vast majority of the precision, on this reciprocal in particular, ends up being shifted out. That's something we'll optimise for later on, but for the purposes of planning an approach, let's see if we can pare this down a bit. What this example does show well though is the effects of left shifting on the resulting reciprocal. Looking at the lines here, you can see that the hex result gains an extra digit at each marked point, yet the row above has completely different hex values. Same again above that, and above that, but then every 4 rows the pattern repeats. Well, that's the bit shifting I talked about earlier in action. The marked rows are all 1 divided by 134. Then the next row beneath is 2 over 134, then 4 over, then 8 over, and then, because there's 4 bits per hex digit, it looks like we have 1 over 134 again, but actually it's 16 over 134, followed by 32, 64 and 128. Hopefully this demonstrates again the power of shifting the basic reciprocal to multiply up and down by powers of 2, but also the ability to align and shift our result by individual hex digits when shifting 4 places. And this will all be crucial for when we get to the main event of calculating pi. Anyhow, I'm getting ahead of myself. For now, let's aim for the outcome here, which is 8 hex digits long, and therefore 4 bytes. This value still represents 1 divided by 134 as it has a leading hex 0, but we could also calculate the result 4 rows down and ignore the leading 0, provided we then know we need to place the result carefully within the overall BBP pi calculation. Right, what does 4 bytes do for our task ahead? Oh yeah, that's going to be much simpler to work with. Now what's interesting here is although dotnet treats the quotient as a bit array and it can have as many bits as needed within a single construct, we're limited to 8-bit values in the relay computer. That means we'll need to build the quotient up bit by bit into a byte, and then store that byte and repeat from there, so a loop within a loop. The end result in this example will be the 4 bytes of the reciprocal in memory like so. Cool, our quotient is looking relay friendly then, and our loop counter C looks okay going from 31 down to 0. So that just leaves the A register in the second column, and... hold on. Oh you... It's 9 bits, isn't it? And that's because 134 is an 8-bit number, which means we need 9 bits to allow for the sign bit. Okay. Actually, let's pop back to the dotnet code. I think I've got an idea. So here's where we just were, and let's look at iterations 15 and 16 side by side. We can see here at k equals 16 that by the time we've right shifted the intermediate result, we're only increasing the final hex digit by 3. And scrolling down a bit, we truncate the hex value to 17 hex places, which is the precision required to arrive at 20 places of pi in decimal. Anyhow, it turns out we don't actually need that final iteration, it makes no difference to the output, and here's the happy coincidence, At k equals 15, the largest number we need to divide by is 126. Bingo. That'll fit nicely in 7 bits or 8 bits with that sign bit added. Okay, let's tweak the k loop and give it another try. And there we go, same result of pi. Excellent. I think for our worked example then, we'll go with 1 divided by 125 instead, as that looks a bit more interesting binary-wise. Let's set verbose on the third fraction then, and give it another run. Ah yes, we also need to tweak the reciprocal routine to work on 8 bits rather than 9. So our sign bit check is looking at the 8th bit now. And we're masking similarly. And same again. And then finally we'll just tweak the output at the bottom here. And then we can run again. Unfortunately pi is still pi, and scrolling up, there's the reciprocal of 125 that we're after. Right, back to the slides. That's better. Our quotient still fits in 4 bytes, but now our A register is 8 bits, which means we're in a good position for devising an approach for this on the relay computer. Right, so we've got our expected result and how it builds up. What else do we need? Well, let's bring in the relay computer's architecture diagram, and our dotnet code, and finally our non-restoring division table from earlier. Even though it's for different values, it'll keep us on track for what's needed. Right, just as in our long division approach, we'll need to set up the registers and prepare some values. Firstly, we'll need somewhere to store our result in memory, and we'll need 4 bytes in this case. As always, we have to assume any memory slot has random garbage in it, so for this example I'll make a sloppy Silence of the Lambs reference and initialise my memory with a nice Chianti and fava beans. In terms of location, let's go with address 20 hex in the 0 page, and let's put that in the M register. Just as with other long operations, we'll need to know when we're done, which here is after 4 bytes. So we'll load B with 4, which is the length of the result we'd like, and then just as with long addition, we can bring M2 over to C, add together to D, and then stash that in Y, which will then be our stop address. That is, 1 after the 4th byte at address 23 hex. What else do we need? Well, we'll also need our divisor value, and I think I'll bring that in via M1, using the 16-bit load immediate trick I used in long addition at the bottom here. If you're not familiar, it can take 2 bytes and pack them into a single 16-bit value, which is a handy way to quickly load M1 and M2 in a single operation. In our case, we want a literal of 125 in M1, which is 7D in hex, followed by the start address of 20 in M2. With M1 populated, I'll then copy that over to X, ready for when we need to add the divisor. We'll also need to subtract the divisor, which I can quickly calculate out in advance as a 2's complement. So copy M1 to B, logic not to D, then copy D back to B, increment to D, and finally I'll stash that in M1 for now. You can perhaps see that we're already running out of registers, and we've barely begun, so whenever we need to store a byte in memory, we'll have to temporarily move the negative divisor somewhere else out of M1, and because of all that, we'll be assuming the memory location will be in the 0 page. Right, we've realistically only got 2 registers left, and these will be the most active ones, so let's use A for the remainder accumulator and D for the quotient byte. So let's clear D and A, and let's label things up so we don't go stark raving mad. I'm also going to break out the binary equivalents of A and D, so that we can track the bit values of the accumulator and quotient as we go, and we'll also want to track the A or U flags. Magnificent. Busiest slide ever. I did say this was going to be a challenging episode though. Anyhow, I mentioned that we're going to need to build up our result byte by byte and bit by bit. For the bytes, we've got an outer loop ready to go with a stop address in Y. But how about that inner loop, where we'll be building up the 8 bits of each byte? Well, again, we're flat out of registers, which would usually lead towards switching things in and out of memory. However, there's a trick we can pull on the quotient byte in register D with a sentinel bit. You what? A sentinel bit is where we set the least significant bit of register D. We'll do that via a set AB of 1 to register B, and the purposes of this sentinel bit is to track when we've completed the current quotient byte. Each time we shift register D, that sentinel bit moves one place left, and when it reaches the most significant position, it'll trigger the sign flag of the ALU. At that point, we know we're about to fill out the last bit of the byte, and straight after, we'll be storing the byte to memory. That is, we'll have reached the end of our inner loop. Actually, to set this up, I think what we'd do is set B to 0 and then increment that to A and then copy that over to D. Why? Well, we want 1 in both A and D to begin with, but we also want to put the ALU flags into a known state. So here the increment will effectively clear all the flags. If we didn't do that, the flags would be as per the last ALU operation, which could be anything. So again, we want to set everything up just so in an unknown state. Just as with initializing memory, it's best to start from a known position. To not do so is inviting in intermittent or seemingly random bugs, which are a pain to track down. So that's initialization done, and so far we've loaded M with the divisor and start address, loaded B with the result length, 4 in our case here. We've then copied the divisor in M1 to X, set our stop address in Y, pre-calculated the negative divisor into M1, set A to 1 for the 1 in our 1 divided by 125, cleared the ALU flags, and finally set the sentinel bit in register D. Cool, I think we've reached a good starting state, and we can move on with a bit-by-bit inner loop. At the start of the iteration, register A will hold our accumulator value so far, and the sign flag will be updated for A's current value. So here the sign flag is clear, and therefore we'll be subtracting the divisor on this iteration. As mentioned earlier, we're going to split the left shifting of A and Q, and for the moment, we only need to shift A. Now my relay computer doesn't have a native left shift, only a circular left shift where the most significant bit will rotate into the least significant bit. But that's no bother, as we can achieve a true left shift by multiplying A by 2. We don't have multiplication either, of course, but to times a value by 2, we just add it to itself. So copy A to B and C, then add back to A. And with that, A is now twice as much, with a value of 2. We can now subtract our dividend by adding the negated divisor held in M1. So we copy A to B, M1 to C, then add back to A for a result of 85. As a result of the operation, our ALU sign flag is now set. Okay, let's quickly recap the logic for this part. And based on the sign flag, we'll be adding if set and subtracting if clear. In both cases, we left shift A and then add the divisor in X, or subtract by adding the negative divisor in M1. That looks fine. Okay, next, based on the new state of the sign flag, we need to decide the next result bit for the quotient. I think we'll start by clearing the C register, which we can do by copying C to itself. And then if the sign flag is clear, we can load B with 1 and copy it to C in preparation for a next quotient bit of 1. Here the sign flag is set though, so we skip all that and leave C as 0. Logic-wise, that looks like this. So if the sign flag is set, we're clearing C, and if the sign flag is clear, we're setting C with a value of 1. Right, we now need to get that bit held in C over to our quotient in register D. We copy D over to B, but before we add C, we need to test for that sentinel bit. To do this, we perform a junk operation to set the ALU flags. So in this case, we'll do a logic OR of B with C into D. That clears the sign flag as the sentinel bit hasn't reached the most significant bit of the quotient byte yet, and at this point register D is now considered mutated. In our example here, the value of D actually is okay, but if register C, the next bit to set in the quotient, was 1, we could have an unexpected value in D because of the logic OR on B and C. We play it safe either way, consider D mutated, and our true quotient value is now in register B. At this point, if the sign flag was set, then we've come to the end of our inner loop. So to recap the logic again, we perform a junk operation to set the sign flag based on the current quotient byte in D, and then if we're sign set, we exit the inner loop, but if not, we continue. And in our example here, that's the case. Our sign flag is clear, and we'll continue the inner loop. Next then, we want to apply the bit in C to the quotient, and first we'll rotate B left into D, and that moves our sentinel bit one place left and makes room for the next bit of the quotient. Note that it's fine to rotate here, as we know for sure that the most significant bit of the quotient is 0, and bringing 0 into the least significant bit of D is as wanted. We're finally ready to apply the bit held in C. So we copy D to B, and add B and C together back into D. In this case here, our quotient D is unaffected because the quotient bit in C is a 0. Logic-wise, we have the following. And we've now reached the first outcome of our reciprocal example at the top right here. And don't worry, I'm going to pick up the pace a bit now, as this episode is dragging on a bit. Last thing we need to do in the inner loop is set up for the next iteration. All that's required for that is to set the ALU flag according to the current accumulator value. And we'll do that with another jump operation by copying A to B and then a logic call back to A, and because that includes register C, which could be a 0 or 1, register A is now considered mutated, so we need to restore A by copying from B to A. That probably sounds a bit contrived, but we've no other way of setting the ALU flags. It needs to be some ALU operation, and whatever we choose, it'll mutate the value in A, so we need the restore. The end of the inner loop is therefore as follows. Right, we're ready for going around the inner loop again. We check the sign flag, it's set, so we'll be adding the divisor in a moment. First though, we left shift A as before, and from this point on I'll skip showing the contents of the B and C register unless needed for the explanation. But of course, to add the divisor in X to the accumulator, we copy A to B, X to C, and then add back to A, which results in 87 hex, and our sign flag is set again, which means our next bit is 0. And just as before, we shift D left and apply the 0 bit. That brings us to the second row of our example top right, and we're still on track with a matching accumulator and quotient, ignoring the sentinel bit. Next, we set up for the next loop, setting the sign flag, and then by the end of the iteration, we get to here. Okay, you get the idea for the inner loop. Let's quickly step through to the point where the sentinel bit test has set the sign flag, and we're about to set our last bit of the byte. Okay, here we are, and the test of the sentinel bit has set the sign flag. We've got our current accumulator A value as expected in the 8th row of our example results top right, and C is holding the last bit of the byte which we need to get into D for a first quotient byte of hex 2. To get that in, we need to left shift D and then logic OR the bit in C. However, we've got a bit of a problem now. This isn't quite the position we'd be in at the sentinel bit test. It's this instead. Because we copied the quotient to B and did a logic OR with C to test for the sentinel bit. As such, register D is now considered mutated and B has our real quotient byte. Somehow we need to left shift B, but we can't add B to itself as before because we need to preserve the next quotient bit in C. Our only option really is to rotate B into D like so, and our quotient in D now has a leading 7 bits correct, with the sentinel bit now rotated into the least significant bit. Next, we'll copy D to B and add B and C together back to D, and our quotient D will now always be 1 higher than it should be, regardless of the value in C, because of the included sentinel bit. But now we've freed up our B and C registers, we can copy D to C and load B with -1, and then add those together back to D to effectively subtract 1 from D. Let's check the logic of this part. After those 3 steps, register D will contain the first complete byte of our result, so we need to place it into memory. To do that, we need to copy our negative divisor in M1 somewhere safe. Let's take that over to C, as we're not going to need the ALU for a bit, and we can then clear M1. And we can then store D in memory, and that's our first byte complete. With that done, we can put the negative divisor back into M1, and we now need to bump M2 to point at the next byte in memory, which we can do by copying M2 to B, incrementing to D, and then copying D to M2. This of course overwrites the last quotient byte in D, but that's fine, as we'll be computing the next one shortly, and it's the accumulator in A that needs keeping safe for the next iteration. So that was a store and increment as follows. Next we need to check if we completed our outer loop, which we do by copying D to B, Y to C, and then just as with long addition, we do an ALU exclusive OR into D to compare the values. That results in 05 hex, because the 2 of 21 and 24 matches, so we get a first hex digit of 0, of the second hex digits 1 and 4 result in 5, because exclusive OR means a bit in one of the values, but not both. Logic-wise again, that's as follows. So compare with the stop address and exit the outer loop if they are the same. That is, if the 0 flag is set. The result in our example case here is non-zero and the ALU 0 flag is clear, so we're not at the end of the outer loop. As such, we're heading for the next byte of the overall result, so we need to set ourselves up for the inner loop. So we load 1 into quotient D via register B, and then we need to set the sign flag based on register A, which we'll do by copying A to register B, incrementing to A, and then restoring A. Again, a junk operation purely to set up the ALU sign flag. Right, I think that's pretty much it, to be honest. And the inner and outer loop work exactly as shown so far, and so if we jump to the final iteration, where we have all 4 bytes complete, we would then increment M2 and compare with Y like so. And the result of the comparison's exclusive OR would be 0, 0, because B and C are the same, and as such the LU0 flag is then set. And we've completed the outer loop and can finish. Let's take a look at the overall logic flow. And there we go, non-restoring division, bent and twisted to fit within the confines of my relay computer, and all ready for coding up in assembly. That's going to have to be for next time though, and we'll pick up where we left off here, code up in assembly, and then give it a run. You might also be thinking, if you've made it this far in the video, that this approach is a bit long-winded, and is likely to be slow because of the loops within loops. I'd agree, and so next time we'll also see if there's any optimizations we can make and take a look at the effect of them. All being well, we can run it on the relay computer, and then that'll be long division in the bag, and we're finally ready to start coding up the full pi calculation in assembly. So, lots to look forward to hopefully, but for now, as always, thanks for watching, and I'll see you next time.